Okay, what we have here, I have a little laser pointer, and taped to the front of the laser pointer is a human hair. And that human hair came from my head. And so I know it's a human hair. So what I'm doing is I'm shining this onto the board. There we go. To show that when the light hits the hair, it diffracts. You see all the little dots coming out to the right and left side of that pattern? That's called a diffraction pattern. It's because light, just like when light goes through a slit, it spreads out and makes that diffraction pattern. The same thing happens with a hair. A hair is sort of like an anti-slit. It has the same mathematics involved. So my hair has a certain thickness, and it's the thickness of the slit or the hair that determines the spacing between the dots, the interference, the diffraction pattern dots. So what would happen if instead of a hair, we use something thicker? Something thicker should make a pattern that's not as far spread out as the human hair. So now we're going to bring in something a little bit thicker, a wire, and see what its pattern looks like. Okay, on this laser we have a copper wire, which is much thicker than what we have on this laser, which is a human hair. Now, if you look at the diffraction pattern on the board, the one above is the human hair, and the one below is the copper wire. So the basic principle that you need to understand here is that the thinner the wire, the thinner the hair, the more widely spaced the diffraction pattern is. The thicker, like for the copper wire, the more tightly spaced the wires are. The general principle is like for a slit, the narrower the slit, the wider the diffraction pattern. The wider the slit, the narrower the diffraction pattern, and the closer together all the dots are. That's the basic observation here. When we were looking at the hair and the copper diffraction patterns, you need to go back and look at that. And on your data page, page 75 in the lab handout booklet, there's a space for sketching the copper diffraction pattern and the hair diffraction pattern. And you need to notice which one has closer spacing and relate that to its thickness. So you'll need to notice that for the thicker copper wire on your sketch, the dots should be closer together. For the thinner hair on your sketch, the diffraction pattern should be farther apart. Okay, so what we have is two hairs very close together, with the bottom being a little closer than the top to make a skinny V. And what that gives us is an interference pattern with the light coming from each hair interfering with itself to give the little teeny tiny dots. So the big dots are the diffraction pattern, and inside of that we see the little dots, which is the interference pattern. And then notice that as we scan the beam up to the wider part of the V, everything gets closer together, and the bottom of the V, everything gets farther apart. Which shows it for interference, which is different from diffraction. For interference, the closer the slits are together, the wider spaced the interference pattern is. Farther apart near the top of the V, the interference pattern gets closer together. That's exactly what's happening here. Okay, so what you should draw in the space on your data page where it says interference pattern near the bottom of the V, you can see where the dots are farther apart. And near the top of the V, oops, isn't that beautiful? Well, near the top of the V, they're closer together, farther apart. closer together. So somehow if you can just sort of sketch what you see there in those two spaces and relate the distance between the dots and the spacing between the hairs. That's the basic principle that we're... All right, so what we have here is a little piece of film with a bunch of lines. Some of the lines are farther apart, some are closer together. So in the space on page 76 of your lab handout booklet, where it says coarse grading, the coarse grading means the lines are far apart, and you can see that for the coarse grading, how close together the dots are in the interference pattern. So you need to sketch that as best you can in that space where it says coarse grading. I'll give you a couple of minutes to draw that sketch. And then as we move over to the fine grading, where the lines are closer together, now the lines on the film are very close together, but the interference pattern is far apart. So try to sketch that in the space where it says fine grading as best you can. Okay, that's it. Now we have the laser with the human hair taped in front, shining onto the board. So there's a relationship between the distance from a slit to a screen. And the greater the distance, the wider the diffraction pattern. Also, the narrower the slit, in this case a human hair, the wider the diffraction pattern. There's a formula that relates those. So what we're going to do now is actually look at that diffraction pattern and do the measurement of the distance to the screen and the distance to the second dark spot. I'm going to put that pencil in front to stop the central spot. There we go. Okay, so we're going to measure the distance from the hair to the board. That'll be the distance L, capital L.
It's 164 centimeters.
Okay, so L is 164 centimeters. Now we're going to measure the distance from the central bright spot to the second dark spot. So N will be 2 in the formula for interference pattern.
3.3 centimeters.
3.3 centimeters to the second dark spot of the interference pattern from a human hair. Okay, so you need to write those numbers down on your data page where it says distance L from the hair to the screen, and then the distance X, the second dark fringe. And there's a formula in your lab handout booklet to show you from that how to calculate the thickness of the human hair. And it should turn out to be somewhere between probably 5 and 10 microns, or millionths of a meter. Okay, what we have here is just a regular CD-ROM with a laser shining onto it. And the CD-ROM has lines like the grooves in a record, only very, very much smaller, about 1.6 microns or millionths of a meter. And we're going to attempt to measure that distance. We're shining the laser onto the CD-ROM, and it acts like a diffraction grating. It's actually spreading the light out, diffracting it out into a wide diffraction pattern. Remember the general principle, the closer together the lines are, the farther apart the interference pattern. So this is actually an interference pattern. So what we're going to do, probably don't even need to dim the lights for this. We're going to measure the distance L from the CD-ROM to the screen. And you can write that down on your data page where it says distance L from disk to screen, estimating separation distance.
146.5 centimeters.
146.5 centimeters is our distance L. Then it says to measure the distance X from the first order maximum from the central bright fringe.
Central bright fringe.
Central bright fringe is there. And the first order maximum,
This is 63.5.
63.5. Okay. That gives you enough data to calculate using the formula in your lab handout manual to calculate the distance between the tracks on a CD-ROM. And it should come out to be, as I said, about 1.6 millionths or 1.6 times 10 to the minus 6 meters. But to do that, you need to know the wavelength of the light. Very critical. So it turns out that this is a green laser. And the wavelength of green laser light is,
532 nanometers.
thank you, 532 nanometers. That's 532 times 10 to the minus 9th meters. That's the other data point you need for the formula. It's also needed for the calculation of the width of a human hair. All right, what we have here is the laser pointer shining through a diffraction grating. Diffraction grating is a piece of film with thousands and thousands of lines really close together, which is making this big interference pattern. Actually, we call it a diffraction grating, but it's really an interference pattern. So this particular film has 500 lines per millimeter. But for your formula to calculate the wavelength of light, what we really need is the distance between the lines, which is called the grating constant. So if you look on your data page, you see a space for the grating constant. You can get that from the 500 lines per millimeter by taking the reciprocal. So 1 divided by 500 lines per millimeter will give you the distance between the lines in millimeters. So you need to calculate that and write it in that space. The other data point we need is the distance L from the diffraction grating to the screen. And if you don't have a space to write that on your data page, just fill it in there and write the distance from that's the distance L,
37 centimeters.
37.0 centimeters from the grating to the screen. Okay. We're also concerned with the spacing between the dots. What we really want is the distance between the first order pattern and the central bright spot. So to get that, we're going to take an average. We're going to measure the distance between the two first order spots and divide by 2.
21 centimeters.
So take 21 centimeters. Is it exact?
Yes.
21.0 centimeters. Divide by 2 and record that as D1, the distance from the first order spot to the central spot. We're going to do another calculation using the second order spot by taking the distance between the two second order spots and dividing by 2.
46.3 centimeters.
46.3 centimeters. Divide that by 2 and record it where it says D2 on your data page. Okay. That's the data that you need to calculate the wavelength of the laser light using the formulas in your data page. And remembering that the wavelength is 530. I think it's 532 nanometers.
Yes, 532 nanometers.
Okay, that's it.